How on earth do you fit 43 unevenly spaced notes into an octave? I'm the classical nerd, and today we're looking at the theories of Harry Partch. Plenty of composers have based revolutionary conceptualizations of music on the idea that something somewhere has gone wrong down the line, and American composer Harry Partch was no exception. He pointed to the hegemonic system of 12-tone equal temperament, and specifically the role that various composers played in establishing this as the dominant tuning system in Western music as the problem. The core problem of 12-tone equal temperament is that a stack of perfect fifths almost fits together, but a B sharp and a C are technically slightly different notes by a profoundly small margin known as the Pythagorean comma. Evening out this comma in a system of 12 notes per octave was, and still is, a huge part of tuning theory from Pythagoras to the present day. Like, we've been dealing with this problem for literally thousands of years. If there was a solution to it, I think we would have come up with it by now. This is especially a problem with keyboard instruments, because they're supposed to be 12 notes. How do you fit them in? Well, in the Baroque era, you had something called mean tone tuning, where you would split the comma up into a couple of different sections, so you would have an arc of fifths as opposed to a full circle of fifths. This rendered certain keys unusable, and all the keys you can use have very different shades. Johann Sebastian Bach's famous collection, The Well-Tempered Clavier, was an endorsement of this new tuning system called well-temperament, which preserved the individuality of keys but smoothed out the imperfections so you could use the entire circle of fifths, because you still had to fit all 12 notes on the keyboard, and prior experiments in mean tone tuning had rendered split key instruments to preserve the distinction between sharps and flats. Like fellow American experimentalist and eventual instrument builder in his own right, Lou Harrison, Partch believed that there was a great deal of value in the pure ratios that were sacrificed for an even circle of fifths, be it in Bach's well-temperament or in modern-day equal temperament, where everything save the octave is either a little or a lot out of tune. Western composers had embraced this system because it allowed you to modulate between different keys, but it sacrificed the individuality of keys, and it sacrificed literally anything except the octave being in tune. Partch thought this was a centuries-long derailment, and his solution to this was ultimately found in a 43-tone, non-equally tempered scale. That is, the notes do not have an even ratio between them. All of them are unequally spaced around the octave. Equally tempered microtonal scales, which go beyond 12 notes to the octave, have often been used as an easy way to conceptualize systems of tuning that might better approximate certain intervals that 12-tone equal temperament can't. These are relatively easy to understand. Understanding 19 equally tempered notes to the octave, now, notating it's a problem, but you can at least conceptualize it because they're all evenly spaced. With a 43-tone unevenly tempered system, you can't even conceptualize it as a 43-tone equally tempered system. So how did he get there? First off, 43-tone temperament sounds neat in the abstract, but when you start getting into the practical realities of notating it or even figuring out how to play it, it gets really complicated really quickly. Take, for instance, your standard keyboard. Let's say we reworked this into 43 tones per octave. 12 does not go into 43 evenly. Actually, nothing goes into 43 evenly. It's a prime number. As a consequence, if you start a 43-tone scale and a 12-tone scale on the same note, none of the other notes, aside from the one you started on, will be the same. Let's say you somehow built a piano with all 88 keys, but you decided to tune it to Partch's 43-tone scale. And let's say you also figured out a way to do this without totally breaking the piano into multiple pieces. You would barely get to 2 octaves. To get the over 7-octave range of a standard concert grand, you would need a keyboard that's 3.5 times longer. And of course, what looks like an octave would sound like some kind of third, limiting the amount that one person could play. Additionally, getting pitches in this system accurate is imposing for players of non-keyboard instruments. And at the time of Partch formulating these theories, electronic synthesis wasn't really in the cards either. To play these, then, Partch turned towards making his own instruments, which were tuned to this 43-tone system. But Partch's life and works can be found in my previous video. Here we're just talking theory. So how did Partch come up with a 43-tone scale? The answer is derived inextricably from his concept of the limit. The limit was his term, but it's been adopted by tuning theorists since, and it refers to how complex your ratios are allowed to go. This is only really applicable in just intonation practices, where you can put an arbitrary limit on the complexity of your ratios. A standard piano just doesn't do this. The ratios are way too far out of whack. The perfect fifth in a just intonation context is a 1.5. It's a 3:2 ratio. It's perfectly in tune with harmonic series. On the piano, this ratio is 1.498307, which is close, but no cigar. The genius of Partch's scale is that these 43 tones are not equally tempered. They're spaced around the octave just so that they manage to hit all the pure intervals. He sacrifices consistency in how far the notes are apart for this limit. The limit is what prevents this from happening, because if there were 43 tones around the octave, you would have some really complicated and really wacky ratios, which you personally might like, but he was all about these consonances. It's an extension of just intonation practices that Western music had abandoned, but expanded to fill all the harmonies that Western music had since accepted as consonances. Part of Partch's conceptualization of music history was an acceptance of higher and higher consonances in the harmonic series. So you went from the fifth being accepted as a consonance, and then the third started being accepted as a consonance, then eventually the seventh started being accepted as a consonance. So basically you were going up and up the harmonic series until you reached a new note, and then over time, over a period of centuries, even that note, that interval, would be accepted as a consonant tone. You see, every odd-numbered harmonic gives you a new note. In music history, it already progressed from 3 to 5, which would be thirds, to 7. 9 is interesting because it's odd, but it's not a prime, so it gives you a ninth, which usually is a new note, yes, but it's not a new ratio. You can just stack two fifths together. This brings us to the 11th harmonic, the first harmonic note that sounds truly out of whack. It's a consonance with its fundamental, that is whatever note is generating the harmonic series, but comes exactly halfway between two notes in 12-tone equal temperament. This is usually approximated by a quarter tone, which gets you within 1/100th of the justly tuned 11th harmonic. This note, Partch noted, was not considered a consonance, and how could it be? It sounds too strange, too whacked out, too out of tune, not to mention inaccessible on any keyboard instrument. Yet according to his theory of historical development and acceptance of higher and higher overtones as consonances, this was the next note that would be accepted as consonants, and its presence defies 12-tone equal temperament. Because 11 is the prime number in question here, Partch chose this as his limit. That is, no ratio, no number within the scale is allowed to be more complex than 11. This was his prime factor. He was not allowed to have a note where the prime factor of a certain number within that ratio was, say, 13. For this reason, Partch's 11 limit embraces more complex intervals than a 5 or 7 limit, just because there are more complicated numbers you can get. For everyone out there who was not paying attention in math class when the teacher was droning on about prime factors, well, you should have. But why stop at 11? Partch admitted this was his own personal taste, and he admitted that you could go up to 13 or even higher numbers. He compared those who did not like 13 limit harmonies to people who thought the tomato was poisonous back in the day. Besides, lower limits could be roughly approximated by 12-tone equal temperament. The 11th harmonic was what defied that system enough that he had to invent a new one to accommodate it. And if you're going to invent a new one, you might as well go further than just the quarter tone system. The genius of his system is that instead of just going up the overtone series and plucking out the notes that he found, he instead flipped the overtone series upside down to create a theoretical concept called the undertone series. The undertone series is not an acoustical phenomenon, like it doesn't actually exist. But he used these to generate harmonies. The overtone series he called Otonality, and the undertone series he called utonality. The undertone series, not being a physical phenomenon, is simply a mathematical one. But here's the cool thing. You can get a just intonation major chord in 5-limit otonality, but a minor chord by 5-limit utonality. Partch used these specifically to describe chords which, as a part of their intervallic makeup, were entirely generated from one or the other. Partch's theories led to the development of his tonality diamond. And despite all these other aforementioned innovations in microtonal theory and terminology, most scholars consider this to be his crowning achievement. but it looks a little complicated to someone who doesn't know what they're looking at, so let's talk through it. Let's look at the 11 limit tonality diamond, which is the driving force behind Partch's 43-tone scale. To achieve this, Partch broke his ratios down into identities, which correspond with every odd number up to the limit, and he sets these up against one another in every possible combination. You can see these reflected in the numerators and denominators of every fraction, which collide in the middle to give us a bunch of 1/1s, or unisons. This generates all possible intervals around whatever your central pitch is. This can be envisioned as a square, but it's usually reflected as a diamond in order to get a line of unisons either horizontally or vertically. But this does not give us 43 tones. If we took these notes and rearranged them in ascending order within an octave, it actually gives us only 29 when we discount the unisons, and the fact that the fourth and the fifth are accounted for on both sides of the diamond. This is the fundamental theoretical basis for the 43-tone scale, but Partch still had to fill it out by using more complex ratios derived from his 11 limit, and filling in what he felt to be large gaps in his scale. In keeping with just intonation principles, he didn't just slice his large intervals in half. Rather, he allowed himself an exception to his tonality diamond rule by allowing for multiples of his limit, or any notes below it. For instance, you could have a 15 show up, or any other note so long as you could divide it and eventually get one of the identities. There are 14 such notes in this scale, which Partch called multiple number ratios. So he wasn't using higher limits. He wasn't using 13 or 17. He was simply multiplying his identities by 2 or 3 to get a ratio that he just couldn't quite reach using the tonality diamond, but fundamentally it is still within the bounds of the limit. While these can't be found in the tonality diamond, you can think of the tonality diamond as just the confluence of the otonality and the utonality of whatever your given middle pitch is. He had to do this in part because if you just constructed a 29-note scale from the tonality diamond, there would be a huge gap between your central note and the next note up, which would be a 12-to-11 ratio. There are 4 notes which span that gap in the 29-note tonality diamond scale, and he did this because if he didn't do that, the space between the central note, that 1/1, and the 12/11 would actually be larger than the smallest note in 12-tone equal temperament. Partch noted in his book Genesis of a Music that the smallest interval in this scale was 14.4 cents, and if you were to take this as your equally tempered distance between each note of the scale, you would actually end up with 83.3 tones to an octave, which proves how much give and take there is in the Partch system between any 2 given notes. The next question is how to notate any of this, which is a huge problem for microtonal composers. Microtonalists who are using a system which divides by 12 can pretty easily map their systems onto the standard 5-line staff. You also have composers like Easley Blackwood and his microtonal etudes that were electronically rendered, where he's basically giving you a key to how these microtones are going to be notated using a standard set of accidentals. Partch's system of notation is complex and it has to be deciphered. The easiest way to notate things would be to take an approach also used by Lou Harrison, which is to include the ratios between notes as well. This is precisely why Partch had to pioneer building his own instruments. Standard Western instruments aren't always capable of playing these notes, and for those that could, let's say that string players aren't generally accustomed to reading a ratio and knowing what distance to move up and down the fingerboard. So was Partch's system, as a child of just intonation, stuck, as some theorists have claimed, in whatever tonic his central pitch happened to be, which in his case was a G? Well, on the surface level, you think the answer is yes, because all the ratios are in tune to this one central G. You wouldn't think that you'd be able to modulate anywhere else, but because he has 43 tones in his scale, from a practical perspective, you actually can. There are enough notes that, to borrow a standard theory term, you can tonicize different key areas, and Partch was willing to do this. You can't just modulate from this vocal pitch to this vocal pitch willy-nilly. It doesn't work like that because it's not an equally tempered system. But that's not the point. The obsession with modulation is what caused Western music to be set into 12-tone equal temperament. According to Partch, this was the wrong way to go. Modulation is not the be-all, end-all of music. Partch's music is also not typically built on harmonic structures. It's about rhythm, it's about timbre, it's about the experience of being in a place where a piece of his is being performed. It's actually ironic that someone who wasn't super interested in harmony would invent a system which had so much harmonic potential that was built from the actual physical acoustical phenomenon of lower and smaller and more simple interval ratios sounding more consonant to our ears. He built a system that pushed the boundaries of what was thought possible, and he introduced a set of terms that is the core language and vocabulary of microtonal and enharmonic composers up to the present day. Like, you can't talk about any sort of tuning system without talking about the limit anymore. And that's all on Partch.